All right, I'm going to continue on here, and now we're going to talk about constant acceleration. Constant acceleration is a special condition that happens when acceleration is constant. It's a very common gravity, or when you're at a stop sign and you mash the pedal to the metal, as I call it. And when you can discover the equations for constant acceleration by taking a is equal to dv dt and putting it in this way, and where acceleration is equal to 0, you see this first constant velocity, or excuse me, constant acceleration equation. If you take v is equal to ds dt, where v now is this term or this expression, plugging that in here, now you can say that here's the expression for position, or this is another equation of another constant acceleration equation. If you take this equation, ads is equal to v dv, and integrate both sides of there, you can see that this is the other constant acceleration equation. And those three forms are used a lot in dynamics. I encourage you to memorize them. They are not that hard to memorize. We use them over and over and over again. And if you have to look them up every time, you do a lot of having to look it up. That's all I'm saying. So, if acceleration is equal to 0, then we have constant speed or a constant velocity. And here's the constant velocity equation. All right, let's do a problem where we have both constant acceleration and constant velocity. Here we have two cars that are pointing toward each other. They are 6,000 feet apart. And this one is constant acceleration starting from 0. And so he's going to accelerate for a little while. And then at this point, he'll be going at constant speed from here to here. This guy starts over here. He's going constant speed the entire time. At some point, after a few seconds or some number of seconds, they smack into each other at this point. And that's what we're trying to find, is where do they smack into each other? All right, let's start with car A. He is under constant acceleration. So this is our constant acceleration equation. V is equal to v sub 0 plus at. At the end of his acceleration period, he's going 80 feet per second. The problem has given, it says that he starts with a 6 foot per second acceleration. And so it takes him t1, or 13.33 seconds, to get up to speed. That's t1. What happens to car B during that same period of time? Well, he's going at constant speed. So if his first 13.33 seconds, he has traveled that far, 800 feet. How far did car A travel in that first t1? Well, using this constant acceleration equation, you can see that he traveled 533 feet. So for the first 13 seconds then, car A has traveled 533, car B has traveled 800. Now they're both going at constant speed. This one is going at, he's going at 80 feet per second, and this guy continues on at 60 feet per second. How do we find out that distance here? Well, let's keep on going. Here I have two constant speed equations. And this one, car A, then is going to go, his position, let's go back and look at our picture. His total position will be this distance plus what he travels here, this one. So let's see what we've got. I'm going to say S2 is going to be S1A plus constant speed after that. Car B is going to go this total distance, which consists of this plus constant speed here. So you add those two together here, and you can just kind of see the way I've done the equation, and you can add those two together. You can say S2 for A plus S2 for B have to be equal to the total 6,000 feet. Plug in these expressions into there. You can see that T2 then is equal to 33 seconds. And then the total distance of S2 is the first 533 plus the 80 feet per second times the next 33.3 seconds. And that gives his collision position at 3,200 feet total. All right, so you can walk through that carefully and make sure you understand how to do that. Let's talk about erratic motion. Erratic motion is when one equation does not satisfy the I guess, a description of the behavior of the motion of a particle. So it needs multiple equations. So I'd like you to watch video 12.3, which kind of goes through a good explanation of that, I believe. So let's just go to an example then. 12.3 goes through all of this stuff. So here's the example. Let's say that car A starts from rest and has the acceleration profile shown in this graph. So in other words, he starts at 5 meters per second for 5 seconds, goes down to 2.5 meters per second for 5 more seconds, and then he goes to 0 acceleration for 10 more seconds. What does the velocity picture look like? When acceleration is constant, velocity increases linearly. Here, acceleration is still constant, and so velocity still increases linearly, but at a different rate. In other words, the slope here is higher because this is higher. When this kind of goes a little bit lower, then the slope is lower. When acceleration becomes 0, then velocity is constant during that time. So the way we construct the velocity graph is we take the area under the acceleration curve. That becomes the change in velocity. So here's what we have. 5 meters per second times 5 is 25. So that means the velocity is 25 at that point. The area under this curve is going to be 2.5 times 5, another 12.5. So 12.5 plus 25 takes us up to 37.5. And that will be our speed at this point. The speed now is going to be constant because acceleration has gone to 0. So that's where our velocity then is flat. If I want to find the position curve during this time, we'll take the area under the velocity curve. So this being a triangle, the area would be 1/2 BH, and that will be the change in position from 0 up to here, which would be 62.5. Are we in feet or meters here? Let me see. We're in meters, yeah. So this would be 62.5 meters here. If I look at from this position to this position, I want to find out the change in position. I would look at the area under these two curves, or these two areas here. So the area here is 125. The area of that one is 31.25. And so the change in position from here to here is the sum of those two guys, giving me the position of 218.75 at time is equal to 10. At the end of the problem, out here at time is equal to 20, I've gone another 375 feet, because that's the area, or sorry, 375 meters, because that's the area under that. So going from here to here is an additional 375. All right, so that's just an example of how to construct the A, S, and V graphs, and we'll be using that a little bit. Now, the last thing I wanted to visit with you about is Newton defined acceleration and velocity as functions of time. A is equal to the v dt, v is equal to the s dt. However, they are often expressed and behave as functions of position or velocity, not necessarily always functions of time. So we may have velocity as a function of s, acceleration as a function of velocity, or acceleration as a function of s. In any of those kind of cases, we will generally look for this equation. ADS is equal to v dv. So let's see what our little problem is here. In this fundamental problem, we have velocity is equal to 20 minus 0.05 s squared. And we want to find out the acceleration when s is equal to 15. So the way you kind of feel this through is if it has time associated with the equation or time associated in the question, then generally you would use one of those equations. However, if time is not in the equation or in the question, then you might want to try this one first. So in this case, we're going to try this. We're going to say acceleration, ADS is equal to v dv. We're looking for something that happens at position, at s is equal to 15 meters. And so I'm going to say ADS is equal to v dv. Velocity here is a function of position, so I'm just going to plug that into here. And I'm going to take that v dv over ds. I'm going to take the ds, put it over under there, but I'm going to separate out the v and the dv ds and just say that the velocity is this, and then dv ds is a derivative of this with respect to s, dv ds. So what is the derivative of this with respect to s? Well, derivative of 20 is 0. The derivative of 0.05 s squared is, or negative 0.05 s squared is negative 0.05 2s. So here I have an expression, and I can multiply all those together, and I get acceleration as a function of position. Now, after you've solved that, then go ahead and solve for what the problem's looking for. At s equal to 15, I can solve that for acceleration. If I want to find the time required to move that 15 meters, neither of these things had time involved, so now we have to go back to look at one of our time equations. So let's try velocity as a function, or if velocity is ds dt. I could put dt on the left side, put that over there, and put v under the ds, so dt is equal to ds over v. When I have v plugged in there, that's a function of position, so I can just do that. Then I can integrate both sides, integrate that side and that side. Over here, I've just got time, so time always starts at 0. In this case, position also starts at 0, so just integrate that, and you get an equation. Now, this may not be as easy to integrate as sometimes, but in the back of the book, there are some forms, and you can try to remember these, or you can just look them up when you need to. I would say look them up when you need to. It's going to be too difficult to try to memorize any of these forms. But this is a log, kind of a complicated log form, and when you do the evaluation, you can solve that for t is equal to 0.929 seconds. So here are some of those integral forms in the back of the book. Again, those are way too many to memorize, and so but you need to know where they are so that you can look them up if you need to. Here's a homework problem that I'd like you to work on, and you can kind of see how they did this. This is the textbook solution, but acceleration is a function of position. So you would start at and what we're looking for is determine the time needed for a rocket to reach 100 meters. So we would start with a ds equals v dv. Since acceleration is a function of s, we can find out an expression for velocity right here as a function of position. Once I find velocity as a function of position, then I can go to v is equal to ds dt and plug it into here to find the time. So it's kind of a two-step process, a little bit complicated. When you get it into this form, you have to look that form up in the back of the book, and you can solve that for t is equal to 5.62 seconds. Now, that's hard, and what I want to encourage you to do is is to master the use of using the integrator on your calculator for these types of difficult things. The calculator won't help you set things up. You still got to do the bulk of this kind of work, but once you get to this form, it can help you do that integral on your calculator. And so I don't have time to show you how to do it, but on Blackboard there is let's see, do I have that here? Yes, I do. Yeah. On Blackboard, I did put under class notes, I believe. I think it's in class notes. There's a little section down here on how to use the TI-83 and 89 calculator for doing integrals and derivatives and some other things we're going to be using the calculator for as we go through there. So anyway, you should figure out how to use the calculator for doing some of these more difficult integrals. The last thing I want to just go through with you is this boat problem. I changed the value just a little bit, but what's going on is this is going to be the acceleration as a function of position graph. Another weird kind of way of doing it, but it's just more of a demo, I guess, to show you that we can solve quite difficult problems fairly easily with graphical techniques and combination with the use of the calculator. So in this case, acceleration is constant as a function of position. A thing to note, or a thing to kind of recognize, if acceleration is constant as a function of position, then it's constant, period. It's also constant as a function of time. If it's constant, it's constant. And so if it's constant as a function of time, then we can use the constant acceleration equations to define the behavior during this constant acceleration phase. So if we want to find out the speed at the end of 100 feet, I can use the constant acceleration equation and see that the speed at 100 feet is 31 feet per second. If I want to find the speed at the end of this thing, which is 125 feet, I want to find the speed at 125 feet, now I have to do this equation. Well, first, I guess let's find out how much time it took. Using, again, the constant acceleration equation, I can see that it took 6.32 seconds to go 100 feet, and my speed at the end of that time was 31.2 feet per second. To find out a little bit more, if I want to find out the speed at 125 seconds, then I can't really go down here. So let's let me see if I can pull this up. I can do this with my fingers here. Anyway, so in that, between 100 feet and 125 feet, this equation applies. And this would be an ADS equals VdV equation. Set the problem up like that. Integrate both sides, noting that my beginning speed for the end of the problem is 31.6 meters per second. Then I can find out the speed at the end of 125 feet. So sorry, the problem, I needed to have a little more paper on my PDF here for you to see the whole problem and me pointing on it. But I hope this is a good enough explanation for you to get started with the stuff we need to do. So, all right, best wishes to you. I'll see you on Thursday.